Better change this to be not last. It should be Fermat first.
Is
that last?
we went with some of my students. They had some heavy rainfall and there was no light. And at the same time, they couldn't on the generators because of some failure in connections. So the seminar couldn't hold, it was postponed indefinitely. But having already took my time to prepare the talk, I feel I should at least present it here in the department. So originally, the talk is meant for a general audience, not necessarily mathematicians. So I try to actually avoid too much of technicality in the talk. So as it is announced, the title of this presentation is an overview of Fermat's last theorem. Actually, from the title, I'm very sure the title is clear, because I had one of the prominent mathematicians, Michael Atia, saying if you are delivering a talk to the general audience, you should try as much as possible, at least the title should be clear to everybody. Even if the content of your talk is not clear. So, an overview, I'm just going to give you a brief account of what Fermat's last theorem is and how it was solved. So I will talk about a little about the background, then statement of the theorem itself, history of its solution, because it has a very long history. It's a problem that lasted for over 350 years before it was solved finally in 1994 by Andrew Wiles, a professor in Princeton University. And then I will say something about elliptic curves. These are objects that were used in establishing that theorem. And then some remarks on the proof given by Wiles. So in mathematics, the problem of solving algebraic equations, polynomial equations in particular, goes back to Babylonians, nearly about 4,000 years ago. Actually, there are ancient Babylonians clay tablets that were discovered. And these things, some of the tablets are preserved in Columbia State University Library. And in some of these tablets, we found formulas that indicate solutions, talking about solutions to what we know as Pythagoras theorem. So this is showing that, in fact, this is done almost 1,000 years before Pythagoras himself. So actually, from all indications, Pythagoras was not the first to prove Pythagoras theorem, even though the theorem is attributed to him. And so in those times, the title, okay, let me write. So, well, my last theorem. So in those days, the main concern, mathematics is all about solving those differential polynomial equations, actually. Equations that are now called Diophantine equations. Polynomial equation in any number of variables, 2, 3, 4 variables, any degree. And about 2,000 years ago, Diophantus of Alexandria wrote a book. His book is called Arithmetica. That's the name of the book. And inside that book, the book contains some formulas or proof that the Babylonian formula given for the solutions of the equation x squared plus y squared is equal to z squared. This is what we call Pythagoras equation. And the problem is that of solving this equation in integers. Actually, this is saying, you know, we know this is very well known to us, that in a right angle triangle, the sum of the squares of the opposite side is actually equal to the square of the hypotenuse. So that book written by Departmental Arithmetica contains proof of the solution of these equations. So in fact, Babylonians, they have already solved this equation. They provided formulas to find all the solutions. There are infinitely many solutions, but then they provided description of how to calculate all the solutions. So it was that book of Departmental that Fermat was reading when he made his remark that led to his last theorem, which we call Fermat last theorem. So in the copy of his Arithmetica, Pierre de Fermat wrote the following statement. He said it is impossible to separate a cube into two cubes or a biquadrate. Biquadrate is the fourth power into two biquadrates, or in general any power higher than the second into two powers of like degrees. So what he was saying in essence, actually during that time, that was in 1637, they don't have the symbols were not available. No algebra was there, nobody was writing even numbers. The symbols are not even available. Nobody knows about 0, 1, 2, 3, and so on. So at that time, they just write mathematics in statements like this. So, but in actually present notation, what Fermat is saying is that you cannot find set of integers x, y, and z such that x to power n plus y to power n equal to z to power n, or any n greater than 2. So this is what he was actually claiming. And the surprising aspect of his claim is that, you know, he was, in his copy of the book, he wrote at the margin, and he said, I have discovered a truly remarkable proof, which this margin is too small to contain. This is a serious claim, actually. He claimed that he has a proof to that statement, that you cannot find set of numbers x, y, and z that will satisfy this equation whatsoever, the set of integers. And he said he found a proof that the margin of his book is too small to contain that proof. And surprisingly enough, when the proof was supplied by Andrew Wise in 1993, he claimed that the margin could not contain the proof is true. What we don't know yet is whether he really has the proof.
You should have gone around
Because
to
the
tell us.
proof
Because
is
I know
over 139 pages.
Bilal.
That's perfect. Okay, sir.
Welcome, sir. So actually the proof is 129 pages. Clearly, the margin of Fermat's copy of Arithmetica could not contain that, couldn't have contained that. So that is actually what we are going to talk about here. So to solve the problem, actually the first significant contribution to solving that problem was made by Fermat himself. And that was done in 1640, where he showed that the equation xn or x4 plus y4 is equal to z square has no solution in the set of integers. And by solving that equation, he has solved the Fermat last theorem for n equal to 4, because this is a stronger statement than x4, y4 equal to z4. If this cannot be solved, then that one can also cannot be solved. But if if you have solution x4, y4 equal to z4, then you can write z square as z1. And then you will see you have. So this is actually what he solved. And he used a method which is now referred to as infinite descents. This is a method of maybe assuming that there is the smallest z satisfying smallest x, y, and z, with z being the smallest integer satisfying this. And then he discovered that if you make that assumption, you will still find another z smaller than the one you assume. So this is an infinite descent. You continue to find a sequence of smallest terms, which is never ending. So this is called infinite descent. We have seen this technique is now being used in many instances. For example, when we are teaching calculus, if you are trying to show that no integer, the square root of 2 is not a rational number, you assume it is p over q, with p and q being the lowest, and then you discover that you eventually find another set of p1 and q1 with the distance. So that was a technique actually developed by Fermat since 1640, and he used it to establish the proof. But then the overall effect of his proof of this one now, because he has now proved that this equation has no solution. So because of the fundamental theorem of arithmetic, this was due to Euclid very long time ago, who showed that every integer is a product of primes. So if you are talking about integers greater or equal to 3, then you realize that all of the integers are either product of primes, actually odd primes, or they contain a factor of 2. And then, so if you have proved the theorem for 4, then you have ruled out all even numbers that contain multiple of 4. All numbers that contain multiple of 4. Because if the theorem is not true for 4, it will still not be true for all multiples of 4. This is a simple consequence that can be seen. And so, which means if I can prove the theorem for 3, I can conclude that all multiples of 3 will also fail to satisfy. The theorem is true for all multiples of 3. So this means the theorem is reduced to only the case of odd primes. So we can decide to assume that Fermat's last theorem is a statement about only p here. That is, we can talk about only p where p is greater or equal to 3 prime, odd, and it should be an odd. How about odd prime is always the ones greater or equal to 3. So he has actually reduced the theorem. The consequence of his proof for n equal to 4 is reducing the theorem only for prime greater or equal to 3. But then in 1753, Euler actually looked at the case for n equal to 3, and he was able to prove Fermat's last theorem for n equal to 3. But that was in the 18th century. In the 19th century, since that time, nobody has ever tried approaching the theorem because it is a very difficult theorem. Nobody could ever know how to even approach the Fermat last theorem. But in the 19th century, around 1816, there is French academy. They offer prize solution of that problem, to encourage researchers to work in that line and see whether it can be solved. We will talk about application actually later on, because you wonder why offering prize to a problem that you don't know its usefulness. But we will talk about applications later on. So when the prize was offered in the 19th century, it became an encouragement, and people now start looking at that problem. And there is this great mathematician, female mathematician, Sophie Germain. She was, during her time, I think she was born in 1776 and died in 1831. Around 1820, she looked at this problem of Fermat and tried to solve the theorem, and she used some clever techniques which she invented actually. She looked at all primes P for which 2p plus 1 is also a prime number. And this type of primes, the later were called Sophie's prime. Like 3 is such a prime, because 2 3 plus 1 is 5. So it's also a prime. Like 5 itself is a Sophie prime, 11, 23, 29, 41, all these are Sophie's prime. In fact, it is still conjecture in number theory as to whether there are infinitely many Sophie's prime. If you can prove it, it is a great achievement in number theory.
Sorry, what is P?
Prime.
P is a prime.
Old prime.
Prime, an old prime. A prime number greater or equal to 3.
But actually, any number if you multiply by 2, it will give you 1 number. And if you add 1, then you always it is 1 number.
Prime.
Yeah, if you add 1, it will
Not odd.
Prime, not old. Prime.
9, for instance, if you take.
Yes. Not every odd number is a prime number.
Yeah, that's right.
Yeah.
I know.
So 2p plus 1 is always odd, but not necessarily prime. So Sophie,
Prime if peace. Good prime.
what she did was to look at all these primes satisfying this property, for which 2p plus 1 is also a prime. And we have just mentioned a few of them. In fact, the largest known Sophie prime has over 388 digits. But it's still a conjecture as to whether there are infinitely many Sophie's primes. And so what she did was to actually divide Fermat's last theorem into 2 cases. The first case is the case where so xp plus yp is equal to zp. And then she looked at the first case is where p divide at least one of x, y, and z. So p divides at least one of this. And then the second case she looked at is when p does not divide all of the x, y, and z. So it doesn't divide the product. So if p does not divide the product or none of the x, y, and z, she proved that the Fermat last theorem is true for Sophie's prime numbers. This is a huge achievement, not satisfactory. Because she has solved the problem for a very large class of prime numbers. And you remember our remark that once you solve for a prime number, then the also theorem is true for all multiples of that prime number. So it's actually a very big achievement. In fact, she lived during the time of great Gauss. Remember Gauss? We have heard of Gauss. 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 Yes. G-A-U-S-S. Gauss. Yes. She corresponded because during her time, actually, females are not allowed into university at that time, and she used to sneak through the back door to attend lectures. In fact, she would dress like a man and sneak into the university to attend classes. She doesn't care about registering, but just to get the knowledge. And then this is how she continued to do her mathematics. And at that time, she would write her result and communicate to Gauss. And in some of the remarks made by Gauss about Sophie, he says she must have the noblest courage, quite extraordinary talents, and superior genius. This is coming from Gauss about Sophie Janet. In fact, one of her contributions in science is the elasticity, theory of elasticity. So one of elasticity in physics. Yeah. So after Janet, in 1825, there was the work of the Richlet and Legender for the case of P equal to 5. Actually, we just said that 5 is a Sophie's prime. She solved the problem for 5, but only one case, the second case. But she has not solved the other case. But then Legender and the Richlet, they solved the Fermat last theorem for P equal to 5. See, even though they consider only P equal to 5, but all multiples of 5 follow immediately. So sometimes when you, this is a serious achievement if you can consider one prime and just solve for it. And that is all. Then we have the one mathematician. I didn't know much about this guy, Gabriel Lamé. But he even tried to, he claimed to solve the problem in 1847. But then before then, in 1839, he solved the problem for P equal to 7. Fermat last year. But in 1847, he offered a solution, a false solution actually. He thought he solved the problem. What he did was to actually start considering, because this was in the 19th century, mathematics has started developing. In fact, Gauss has already introduced Euler. In the 19th century, Euler had already introduced the notion of complex numbers. And so this Gabriel Lamé introduced complex number into the problem, into that problem. And what he did was to actually divide the equation by ZP, and then he has one here. And then he now writes x over y as x1 and y over x over z as x1 and y over z as x1, and then he has equation of the cycle. And then he was now looking at the solution around the cycle. So he looked at the complex root of unity, and then he was trying to do some factorization there. But then what he failed to realize is that because he changed the domain from, so he was looking at the complex set of complex roots of unity now, heat power in the unit disk. And then if you group all these roots of unity, at that time the notion of group was not actually very well familiar. So he never realized he was working in a group. And the numbers that were prime in the context of integers, in this context, they are no longer primes, they are factorizable. So that is what he failed to realize. And he continued to work with the assumption that they are still prime numbers even in that context. And then he offered the solution, but then when it was checked, it was realized as a false solution, something was wrong. And so that was Gabriel Lamé in 1847. Still in the same year, 1847, Edward Kummer, look at the Lamé's method, and he now said he will classify all these prime numbers, and he tried to introduce what he called ideal numbers. These ideal numbers are what we are calling ideals of a ring now these days. So his work actually introduced the concept of ideals, a ring, and in fact that is what led to the most of the development a ring theory or in abstract algebra in general that we are enjoying today. I define, so what Lamé fails to realize was some prime numbers will no longer be prime in that context. So he tried to now classify all those prime numbers that will remain to be primes. So in this sense, the ideal is not factorizable and something he did that. I don't want to go into too much of technicality since it's like a storytelling. So he defined what he called regular primes. And these are primes that will preserve the primality even there. And he solved Fermat last theorem for all regular primes. And it is still also a conjecture that there are infinitely many regular primes. In fact, it is conjectured that 60% of prime numbers are regular primes. So he has almost solved Fermat last theorem 60%. But mathematicians will not be satisfied when you say 60%. Even 1%, if it is still there, you have not solved anything. So actually, a very serious progress, but still not enough. Then in the 20th century, and this was computer era, now computer science has started coming into picture. And people started using machines, computer system now, to attack the problem. And then there are some of the mathematicians, some of the computer scientists in 1930, 1951, 1977, and 1992, they all addressed the problem. In 1930, Vendiva, he showed that Fermat last theorem is true for all numbers up to 600 using computer program. And then we have Lemma, 1951, who proved Fermat last theorem to be true for all numbers, integers up to 4,000. And then there was another person who proved it to be true. That's very small.
Very small.
And then he proved it to be true in 1977 for all numbers up to 125,000. And then there is Bola et al. It's a group of these people. In 1992, they proved Fermat last theorem to be true for all numbers up to 4 million. Using computer, it's still small. Very, it's not even up to 1%.
Are these guys computer scientists or
They
they
are
are
all computer
mathematicians?
scientists.
Because it is
Well,
the machine that is doing
actually,
it.
in those days, there is no difference between computer scientists and mathematicians.
When you go backward, physicists, there's no difference.
The machine.
Remember, one of
The subjects had not
one of
developed the
the
level.
inventors of computer, as we know it today, is John von Neumann. John von Neumann is not a computer scientist.
No.
Then
Why the
many of them-
computer is sparked
and
out
and so on and so on. So they are just mathematicians actually, but they started using numerical
Pascal, the
approaches,
calculator.
writing programs.
Pascal.
the one.
Story of
Then, in 1993, Andrew Wiles, a mathematician, proved the theorem for all n greater or equal to 2 using modern mathematics, which were developed in 19th and the 20th century. He used purely abstract algebra and some number theory.
That means he has solved. That means he has.
The problem is solved.
That was when it was solved actually. He
Completely.
announced his proof,
Final.
he announced his solution.
But that is 129 pages more.
And
But the number of pages for the page.
Alkali, how many pages?
129 pages.
Yes.
Proof.
So now still there, you know,
So-
it is required that you should be compacting the proof if it is possible.
Pardon?
And if we want people to be,
Yeah.
we want people to be given us 5 pages, 10 pages, 18
If it is
pages.
possible.
If it is possible, that is it.
Yes.
That is it.
So actually, I'm just going to give us a glimpse of his proof. You cannot actually, there is
Not easy.
a mathematician that I saw in one of the news reports. Yeah, okay, actually it is
93 you say go? 93.
1993.
Was he in Cambridge or Oxford?
Princeton.
Because I
Princeton
think-
University, but he announced his theorem in Cambridge University.
Because he came to my university that time
And,
to prove, to tell us something.
I think Professor A. Tijani said he was there when he announced the theorem.
Yes,
At the conference, he was given 3 hours,
Yeah,
3
go
days
around
he went
to
round.
talk for 3
He
hours.
He came to my university, I know.
And he announced the proof. So we are going to talk about that proof actually. So actually what Andrew Wise did, he used pure mathematics. And most of the mathematics he used was developed in the 19th and 20th century. So and that is why what is clear is that the proof provided by Andrew Wise was not the one that was claimed by Fermat. So it's still an open problem to discover Fermat's proof.
Okay, Fermat,
Yes.
give some proof.
Yes.
If at all it exists.
If at all it was there.
Because now, who knows?
He himself was not 100% a mathematician.
Fermat is a
Was a
lawyer.
lawyer.
He was a lawyer.
Ah.
Yes.
I know this one. Oh, this is
Lawyer and a vicarious in mathematics.
Fermat was a lawyer, actually, not a mathematician. And we don't even know when he made that his remark, because he didn't publish anything. His notes were published by his son
Yes.
after his death.
After his death.
So nobody can say exactly when he made that remark, actually. And he was a lawyer, but he had so many theorems, and still, in fact, so many
Curious in
theorems.
mathematics.
I saw so many results.
Fermat's last theorem is
It
not
is a
his
lot
last
of
theorem,
mathematics.
actually. It was called, the reason why it was called theorem is because he claimed to prove it. So it was not called conjecture because there was a claim proof.
Yes.
People are not aware. They are just trying to discover it, the proof.
Yes.
So not to
So
prove it.
he
And there
was not alive.
and it's not the last, and it's not the last of his conjectures. Actually, he made so many conjectures after Fermat's last theorem. But the reason why it was called Fermat's last theorem is because it's the only one that's stayed long for people to be able to before it could be solved. Over 350, about 358 years before it was solved. Because 1637 to 1992. So, well, I will just talk a little bit about the approach made by. So, well, I have to be a little bit fast, and maybe I will have to talk about some definitions of terms at this point. So, in order to understand the proof presented by Andrew Wiles, we need to actually define some concepts. The concept of elliptic curve. The elliptic curve actually is these are just cubic polynomials in two variables. Any polynomial in two variables that is cubic is called an elliptic curve. And these polynomials, if they have rational solution, if they are rational solution, you can do some change of variables, and you can write them in the standard form as y square is equal to x cubed plus ax square plus bx plus ax plus b. It can always be written in this form. This is called Weierstrass normal form of the elliptic curve. You can do some transformation of the coordinates, and you'll be able to arrive at this nice form of the solution. If you take elliptic curve and plot the graph in the complex domain, you will see that the graph of an elliptic curve will look like the surface of a donut or a torus. The surface of a donut, something like that. Like what is it called? The tube of tire. Something like that. But when you plot the graph in the real domain, in the real line, the graph will look like this. Actually, because it will look like something like this, or something like this. Well, it depends on the shape. Will depend on this cubic equation. If this one is having only one root, then this is the shape, one real root. It has three distinct real roots, and this will be the shape of the elliptic curve. So these elliptic curves, I'm not going to talk more about them, I will just talk about the interesting aspect, the actual interest in solving Fermat last theorem. Because there is the work of Poincaré in 1901 that shows that you can define some group structure on an elliptic curve. And this is a property of the elliptic curve that is not available in other curves. Cubic curves are having this type of property. You can define some group. If you get the set of all rational solutions, it forms a group. And this group is abelian, it's finitely generated, something like that. But then what mathematicians, number theorists are mostly interested in about elliptic curve is in finding integer solutions to elliptic curve. Are there integer solutions? Or if there are integer solutions, how many? How many of them? And then, or can you take a collection of elliptic curves with a certain property or characteristic and study that collection? These are the kind of questions mathematicians ask about elliptic curves. But sometimes solving an equation like this, to solve this equation is the same thing as solving s cubed plus ax plus b is equal to 0. It's the same thing, okay? So, but mathematicians sometimes will, instead of solving this equation, they will reduce the equation modulo a prime. So they will say they are solving modulo equal to 0 modulo a prime. You see, the advantage of doing this is it reduces the number of solutions to finite. Because when you are solving over all the integers, you may have infinitely many situations to look at. But if you are solving modulo a prime, if the prime is 5, for example, you will just end up, you are just looking at from 0 to 4. And that has reduced the burden. But at the end of the day, you will get information about the solution in the integers. For example, where it coincides, anywhere it coincides with 0, it is actually modulo p, and that will give you the actual solution of the problem. So, instead of counting solutions in integers, mathematicians will count for solution in modulo p, actually in the congruence modulo classes. And we donate by NP the number of solutions modulo p. So it was Gauss who first studied this curve, this elliptic curve. Y squared is equal to s cubed minus x. This elliptic curve is a very nice one. It was studied first by Gauss. When you look at the solution to this curve modulo p, so mod p. And we try to solve this curve modulo p. So what are all the solutions where p is a prime number? And the interest is to know how many solutions. This number is actually the interesting part of the. So if p is 2, there are only 2 solutions modulo p, modulo 2. If p is 3, Gauss discovered that there are 3 solutions. If p is 5, there are 7 solutions. If p is 7, there are 7 solutions. And if p is 11, there are 11 solutions. If p is 13, there are 7 solutions. 17, there are 15 solutions. 19 solutions. 23 solutions. 29, 39 solutions. Actually, that was done by Gauss in 1814. In fact, he didn't just look at the special prime instances of prime. He looked at NP and found a formula for the number of solutions modulo p, this NP. Gauss found that for p equal to 2, NP is 2. But if p is congruent to minus 1 modulo 4, then NP is equal to p also. Like we have mentioned, once p is 7, that is 7. 11, that is 11. So anytime it is congruent to minus 1 modulo 4, meaning if you remove minus 1 from the number, it is a multiple of 4, then the solution, the number of solutions because sometimes you don't want, you see, mathematicians at times they are not interested in solving, they just want to know how many solutions are there. Because the solutions are not the most important aspect. Sometimes the equation, and maybe you just get some information about the solution, you can be able to analyze the situation. And if P is congruent to 1 modulo 4, because as all prime numbers greater than or equal to 3, can be categorized as one of these. It's either congruent to -1 or congruent to 1 modulo 4. So Gauss discovered that there is a nice complicated formula. I have not reported the formula here. Very difficult. Some complicated formula, and he used that formula actually. In fact, it is the formula I used to generate my values here in my slides. So based on that formula, this sequence of NP is having a very nice structure. And Gauss discovered it, and because of this nice structure, the curve studied by Gauss was called modular. Modular. So if any elliptic curve is having this nice structure, for the number of its solution modulo, it will be called modular. And this is what we refer to as a modular elliptic curve. But actually, modularity, when you talk about modular forms, it is an aspect of mathematics that's come from a separate branch of mathematics, complex analysis or harmonic analysis. When you are looking at functions, with the modular forms are complex functions that exhibit some very symmetric nature. I have a few graphs, 2 graphs of modular forms. Maybe I will just turn the system so that you can see. This is how modular form is looking like. When you plot the graph, because modular forms are defined in a disk. They are complex functions, but the domain of the definition is actually the unit disk. So when you plot the graph, they have this type of symmetry. A very nice structure. So this is from harmonic analysis actually. And then this number is having a very nice property. So what happened was there are 2 mathematicians, or a mathematician, Japanese mathematician called Taniyama, Yukata Taniyama. In 1955, a conference, he announced that, or he conjectured that associated with every elliptic curve, there is a modular form. Because these modular forms, you can write them as in form of a Fourier series. And in this Fourier series, the coefficient. So what he claimed is that given any elliptic curve, I can always find a modular form such that the corresponding Fourier series, the coefficient of the prime terms will coincide with this number np. Actually not np, but the difference between p and np. And this is unexpected. Actually, who will expect that there will be any connection from something in number theory and the harmonic analysis somewhere? So they didn't pay attention to what he was saying because they felt he was not making any sense, and he was just a student, and so they thought. Japan. He attended the University of Tokyo, actually. And then 3 years later, after he met that, he died in 1958. Then he made this conjecture. Then there is a mathematician at Princeton University who was also a Japanese, Goro Shimura, who looked at what Taniyama was saying later on in 1962. And then he tried to reformulate the claim of Taniyama in a very more modern terms that it will be understandable to mathematicians, and then he published the results. And it became so clear that the connection can actually be established. And so the conjecture, it was a conjecture that give me any elliptic curve, there is always an associated modular form. So it became known as Taniyama-Shimura conjecture. So you can associate with an elliptic curve a modular form. So this is like kind of creating a bridge from one world to some other world, where you have some continents and then you are trying to get from one place to another. Because sometimes in mathematics, when you are dealing with a problem in maybe abstract algebra, it may not be clear what you are doing. But if you can be able to establish a one-one correspondence from that aspect you are looking at to maybe some differential equation where things are clear, you can transfer from the abstract construction to where you have some concrete sense of looking at things. And then when you solve the problem there, you transfer back. This is what we do. This is exactly what Andrew Wiles did, or what Taniyama-Shimura conjecture is proposing. That what we are dealing with in numbers theory as the problem of solving or studying solutions of elliptic curve, if we cannot handle them here, we can go to harmonic analysis and see what we can do there. That there is a one-one correspondence from this aspect of number theory and that aspect of harmonic analysis. And that is Taniyama-Shimura conjecture. So, Taniyama-Shimura conjecture is that every elliptic curve is modular. Now, in 1985, there's this German mathematician, Gerhard Frey. Sorry, I'm not good at pronouncing this. So, he assumed Fermat's last theorem is false. He says, suppose Fermat's last theorem is true. That is, there is some prime number t greater than or equal to 5, for which there are integers a, b, and c, so that a to the power p plus b to the power c equal to p. So he assumed Fermat's last theorem is false. And on the basis of his assumption, he constructed an elliptic curve that looks like this. So what he assumed is that there are numbers a, p, with b, p equal to c, p. And he constructed this elliptic curve with this assumption that there are these integers, and then he constructed x squared minus ap, and then x squared plus bp. This curve became known as Frey's elliptic curve. And he promoted the idea that this curve can be used to prove Taniyama-Shimura conjecture. That this curve, what he is suggesting is that this particular curve, if Fermat's last theorem is false, then this curve is not modular. And if it is not modular, then Taniyama-Shimura conjecture is not true. So this is a counter-example to Taniyama-Shimura. So meaning, if Fermat's last theorem is not true, Taniyama-Shimura is not true. If Taniyama-Shimura is true, Fermat's last theorem is true. And so if somebody can solve Taniyama-Shimura, then he has solved Fermat's last theorem. That's what Andrew Wiles did. He never looked at Fermat's last theorem, he was solving Taniyama-Shimura. This was an idea promoted by Frey, but it's just a claim actually. He claimed that this curve is not modular. But in 1985, a year after, an American mathematician, Ken Ribet, proved that this curve is actually not modular. And then, so which means he has settled the claim by Frey. So meaning, if somebody can prove Taniyama-Shimura, then he has proved Fermat's last theorem. And that is what Andrew Wiles did. So what Andrew Wiles did was to look at this curve. And he now look at this curve, and he realized that this curve belonged to a class of elliptic curve that is called semi-modular. Well, it's a complicated bunch of definitions I'm not going to use. It's called, not semi-modular, so it's semi-stable elliptic curve. It's called semi-stable, which is a whole class. So this is part of the class of elliptic curve that are called semi-stable. So instead of concentrating on this, he just concentrated on the class of all semi-stable elliptic curve. And he showed that that was what he announced in 1993 at Cambridge, June 23rd. He announced that he has proved that every semi-stable elliptic curve is modular. So this is a contradiction because Ken Rivet proved that it's not, this curve is not modular. And Andrew Wiles' result is now saying it is modular. So the only conclusion is that the assumption upon which this curve was constructed is not true. And that assumption was to assume Fermat's last theorem false, which means Fermat's last theorem is true. That was how it was concluded. This is what he did. So,
How will you be able to do something?
so actually that was what settled the problem. There were, and the proof we mentioned is 129 pages. There were some issues actually that arise because this paper was not published until 2 years thereafter. 1995 exactly. I have the copy of the paper because there is this mathematician, Nick Katz. He critically looked at that paper. Actually, Ken Rivet, 6 reviewers. The papers was submitted to 6 reviewers. So Nick Katz critically looked at that paper and he discovered some flaws, some errors, some issues, some assumption. He was working with real rational numbers and he made some assumption. The assumption is true for rational numbers, but somewhere else it may not be true. And then he actually pointed that gap to Andrew Wiles, and Andrew Wiles could not solve it. He was eager to see that he solved. He had to employ the help of his student, Richard Taylor. He was Andrew Wiles' PhD student, and he invited him for postdoc. They sat down together and they wrote a separate paper to fix that problem. And then the 2 papers were published actually in 1 volume. And that was what settled the problem. And then later on, a team of mathematicians, about 5 to 6 of them, they sat down and completed the work of Andrew Wiles. Andrew Wiles showed that Taniyama-Shimura conjecture is true only for semi-stable elliptic curves. But they later on proved that for all elliptic curves, the conjecture is true. And so that problem is settled. There is a remark made by John M. Howe of blessed memory in 2002. He said the truth of Fermat's last theorem is so far as we know. That was in 2002. I don't know whether some people have found something now. He says, so far as we know, irrelevant to the building of bridges, the design of computers, or classification of elementary particles. But actually, the Fermat last theorem itself may not have any direct application, but the proof towards the truth of that theorem has already found so many applications, because we have seen how we transfer from number theory to harmonic analysis, and nobody can dispute the fact that harmonic analysis, there are a lot of applications there. Actually, that paper there is a news report in Quanta magazine by one Michael Harris. This is a news reporter. He said 10 mathematicians gathered at the Institute for Advanced Study in Princeton in a successful effort to prove a connection between elliptic curves and modular forms in a new setting. Not the setting of Andrew Wiles, because it's very complicated mathematics. They had all followed different routes to understanding the structure of Wiles' proof, which appeared when some of them were still small children. if you ask them to reproduce the proof as a sequence of logical deductions, they would undoubtedly have come up with 10 different versions. So actually, this is a serious. This is so actually, even to understand Andrew Wise and explain it in simple terms can lead to award of a PhD degree. That paper only, just read it and understood it and explain it in simple terms, actually is worth awarding a PhD degree. That is what actual mathematics is. It's a very serious, sophisticated mathematics. So there are still some open questions which I will just actually mention here. And then some of them we have already said in the course of the discussion. What was Fermat's proof? The proof he claimed to have, that he claimed that the margin is too small to contain. Because our suspicion is that maybe he has the proof, and that proof should be simple, more simpler than that of Andrew Wise, because during Fermat, there is no all this abstract algebra, all this whatever. So he must have used, if he has the proof, he must have used just simple open close brackets. And so if somebody can discover, it's a serious actually progress in mathematics. So if there are more simplified version of the proof than the one, or using probably techniques other than the ones used by Andrew Wiles, can you prove it otherwise so that it may lead to some other aspects of application of mathematics? And what are the application of the Fermat last theorem itself? The theorem itself, not the proof, within and outside of mathematics. If one can discover its serious progress. And now, with the achievement of the result of Andrew Wiles, we have understood, when I said we, I'm talking about we mathematicians, not. So we have now know more about Langland's program. What then is Langland's program? Actually, this is an idea that was proposed by Robert Langland. He's the person occupying Isaac Newton's office. Now, still occupying the office that was occupied by Newton. And he said, he was proposing this program that we can always be able to achieve any problem in mathematics that you have been struggling with, some of these problems that took this time of time that have not been solved for many hundreds of years. He is proposing that you can always transfer to another area. So if you have a problem in complex analysis you are just suffering with, you could not solve it, transfer to functional analysis. Find a way of transferring that problem to functional analysis. You are dealing with a problem in semi-group theory, find a way of transferring it to dynamical system. You'll be able to achieve it there. So he was saying all problems in number theory can be solved via a 1-1 correspondence into harmonic analysis. And then Taniyama-Shimura conjecture that is solved by not just actually, by Andrew Wise, has already actually achieved. It has supported his claim. So, and that is called Langland's program. But there is still much to know about that program. And mathematicians are still researching to establish connection, between different areas of mathematics. And so that would be a great thing. I think this is what I have to tell you. I thank you all for your patience and your time. Thank you very much.
The advertisement made a remark.
Yes.
What you are saying last, that it can be possible Only where there is no hunger.
He is becoming a Nigerian.
Let me make my festival because Alkali is there. Because when this film came out, I was just back from my
Yes, I know.
some years back from my
PhD.
PhD.
Yes.